All right, thank you for uh, tuning into this class. As you're aware, we've been looking at laws of probability, or rather theory of probability. So today, we look at just two laws of probability, the addition law of probability and multiplication law of probability. Then we look at some examples that I would expect you to do. I also have done a worked out examples rather, and I hope that that will assist you to be able to get and grasp these type of questions whenever we are confronted with. Now, let me begin by saying that we are looking at the laws of probability. As I said, we have two: the addition law of probability, and this is recognized by the word or. Now, if A is the probability of event A happening, and B is the probability of event B happening, then the event A or B, the event A or event B happening will be given by the probability of A plus the probability of event B. This is called the addition law of probability. And I have said it is recognized by the word or. Now, if we have got so many events happening, say A or B or C, up to event N happening, then the total probability will be a sum of those individual events. So it will be the probability of event A plus probability of event B plus the probability of event C until the last event probability of event N happening. In our second law, we have said it's called the multiplication law of probability. And under the multiplication law of probability, again, we are saying that it is recognized by the word and joining the probabilities. So if we have an event A happening and you have another event B happening, then the probability of event A and event B happening, remember the word and will be given by the product or the multiplication of the probability of A and the probability of B. Now, suppose you had so many events happening that you want to find out the probability of event A and B and C and D up to event N happening. What will be the total outcome? According to the law of multiplication, the total probability will be given by the product of probability of A, probability of B, probability of C, up to the last event probability N. Look at this example. An event A happening, the probability is 3 over 5. An event B happening, probability is 2 over 3. Calculate the probabilities of both A and B. That multiplication or addition. Suppose I added, calculate the probabilities of A or B happening. Is that multiplication or addition? Can I go further? Suppose it was only event A happening or event B happening. What would be the probabilities? Think about that. Now, when testing 100 soldered joints, 4 failed during a vibration test and 5 failed due to having high resistance. Determine the probability of a joint failing due to 1 vibration, B, high resistance, C, vibration or high resistance, and D, vibration and high resistance. Remember, we said when you're using or, then it is the addition law of probability. When you're using and, it is the multiplication law of probability. Then I think this you can work it out. That should be fairly simple. Now, I have this worked out example. We have about batch of 50 capacitors. 35 are within the required tolerance. 11 are below the required tolerance. The remainder above the required tolerance. Some simple computation there. 35 plus 11 is 46. So 4 are above the required tolerance. Determine the probability when randomly selecting a capacitor and then a second capacitor. So you're doing in subsequent draws. You're doing subsequent draws, one after the other. What happens when you want to get this probability that both are within the required tolerance values when selecting with the replacement and when selecting without replacement? And here we are saying the first draw is drawn and the second one is drawn above. The first one is drawn below and the one is there. The second one is above. So take note of this question here. 35 are within, 11 are below, and 4 are above the required tolerance values. These are capacitors. Now, how do we solve this? For the first question, we said that the probability of selecting a capacitor within the required tolerance is 35 over 50. 35 over 50. Now, the first capacitor drawn is now replaced, and the second one is drawn from the batch of 50. If it is replaced, it means that you retain the original value. What was the original value? There are 50 capacitors. So even after making the second draw, you have got 35 out of 50. In this case, we are saying that the total probability for drawing the first and then the second would be 35 over 50 times 35 over 50, which is 0.49. So you're picking the first, which must be within the required tolerance value. You replace it back into the batch, and then you select the second. That means that the original value is sustained, and all the capacitors within the required level, tolerance level, are retained. And that's why you have this value. In the second part of the question, we're saying the probability of obtaining a capacitor below the required tolerance is 11 over 50. Remember, there were 11 that were below the required. Now, if you're choosing the second without replacement, so I select but I do not replace, then what would be the probability? There will only be 49 capacitors left in the second draw because it is not replaced. The probability of drawing a capacitor above the required tolerance value on the second batch would be 4 over 49. Remember, the ones that were above the required were only 4. So the remaining would be 49, because in the second choice, there was no replacement. So what would be the total probability? Of course, you're multiplying The ones that are below 11 over 50 times the ones that are above 4 over 49. Why 4 over 49? Because we have said there was no replacement in the second selection. That's why the answer is that. Now, moving to the last question here. You have got 30 taps, 5 are defective. You want to select a tap at random, then you test, and then you select a second tap, again you test. What is the probability that neither of the taps is defective? Neither is this defective. Neither. None of them are defective. With replacement, without replacement. If we are replacing, it means that remember there are 5 which are defective. So you have got 30 minus 5, which is 25. These 25 are not defective. In our term here, we are saying they are satisfactory. So you have got 25 over 30, which is the same as 5 over 6. With replacement, remember, so if you are selecting in the second draw, how many will they be? Of course, you select one and then you replace, there'll still be 30, and there will still be 25 satisfactory. So the answer will be 5 over 6 times 5 over 6, which is 25 over 36. Hope it makes sense. Without replacement, what happens? So I have got 25 over 30, which are good, they are not defective. In the second selection, remember, without replacement, I'm not replacing. Once I pick one tap, I'm not replacing it back into the batch. So if there were 25 which were good originally, and I picked one that was good, there will be only 24 left which are good. And out of 30, there will only be 29 left in that batch because I'm not replacing. Hence, the probability of drawing a satisfactory tap on the second draw will be 24 over 29. Thus, the probability that the first tap drawn and the second tap drawn are satisfactory will be 25 over 30, which is 5 over 6, times 24 over 29. And you get that value, 0.689. Now, this is the same question, but it is twisted a bit. We have 30 water taps, 5 defective. You're drawing a tap from a batch at random, the first and then the second. And you want to find out whether one is defective. Given these conditions, 1 with replacement, 2 without replacement. So what do? The probability of having one defective tap can be achieved in 2 ways now. If you're only looking for one that is defective, so what are the chances here really? So you can choose the first choice or the first draw. You have one functioning or satisfactory tap, and the second is bad, or in the second choice, the first is bad and the second is good. So you have either the first choice, one is good, the second bad, or in the second choice, the first one bad, the first bad is the bad, then the second is good. So basically that's what we're simply saying. So if P is the probability of drawing a defective tap and Q is the probability of drawing a satisfactory tap, then what are we saying? In 2 ways, you can either draw a satisfactory and a defective, or a defective and a satisfactory. That's what we simply say. And therefore, by implication, you've got 5 over 30 defective and 25 over 30 satisfactory or non-defective. When you're looking at one defective, then you're saying 1 over 6 defective times non-defective plus non-defective times defective, which is 10 over 36, which is roughly 0.277. Suppose I had some replacement, without replacement, what would it be? Without replacement, so you pick without replacing, you don't return. So if I pick 1 and I don't return, obviously in the second batch there will only be 29 because I'm not returning. So the first one is 1 over 6, that is 5 over 30, which is defective. And if there were 25, if there are 5 that were defective, then it means that 25 are not defective. In other words, they are satisfactory. That will be 25 over 30, which is 25, which is 5 over 6. In the second choice or second selection, out of 30, and you are having no replacement, there are only 29 in the second draw. So what will be the probability? Sorry, the probability will be, sorry for this hitch. Thank you.